Good evening, everyone. Welcome to the second edition of the Vacuum Transport Seminar of the spring semester 2021. We welcome everyone in the name of Swissloop, Eurotube, the University of Applied Science in Den Leer, University of Oldenburg, TUM Hyperloop, and Technical University of Munich. I would like to give a short outline of our speakers today. So we have three speakers. We start with Dr. Ralf Effenberger. He's the director of Intis GmbH. And he talks about the testing facilities in Germany. Then afterwards, we have Nico Ege. He's a bachelor student in mechanical engineering at ETH Zurich. He talks about rail gap bridging for vacuum transport system. And last but not least, we have Kristen Harvey. He talks about partner nose design experience and how to cater for passengers in fast-moving vehicles. So I would like to hand over to Dr. Effenberger, and you can please share your screen, please. And maybe again, as an information for the audience, I already put the information in the chat. So we collect all the questions on the webpage slido.com. So during the presentation, you can type in your questions there. And after every presentation, we go through the questions and have a short discussion and interaction. You can find the information in the chat. And we're looking forward to your presentation.
Now you can hear me? Perfect. Thank you very much. Good afternoon to everybody. Very pleased to have a second chance to introduce a bit. So last time I had the chance to talk a bit about large-scale Hyperloop testing, possible Hyperloop testing facilities. I don't want to go through everything again because I think most of the audience did already participate at the last conference. If you remember, it was related to giving an overview about the maglev testing facility in the Emsland, which is still existing, which has not been taken away yet. And we are still looking forward to find future possibilities to provide services to high-speed rail applications. Might be maglev as this one, or might be also Hyperloop applications, where then obviously we would have to add something on top of the guideway, which I wanted to show you right here. Or also presented during our last meeting, there are different ways to get the facility converted to Hyperloop applications. Not necessarily from the beginning a tube would have to be mounted on the guideway, because most of the current developments, or most of the current developments are not yet at the stage to run their vehicle on guideways at full speed. So there is still a lot of investigations to be done with the vehicles and the motor, propulsion, guidance, levitation, which not necessarily now has to have a tube on top and to run in vacuum, because many aspects still have to be investigated. Is the control system for levitation, for example, stable? How can you synchronize the motor with the vehicles? That kind of questions. However, one day, if we come to the point to provide services at higher speeds, let's say more than 300 kilometers per hour, then obviously we need to have to put something on top of the guideway, where I have summarized here just a few ideas how it could work at our facility. Currently, the distance between the ground supports is 25 meters. We are not clear yet whether 25-meter long tube elements could be manufactured with tolerances as necessary for high-speed operations. Therefore, there are some ideas here to put some further support stands to the ground, or we may also keep the existing guideway element from maglev, which is the blue sketch in the right corner, top corner, where we may also install something on the existing guideway elements from load point of view, they can easily sustain it because it's not expected that the tube elements together with the vehicle would be more heavy than the so far tested maglev vehicles. During our last presentations, a few questions came up concerning wireless inductive wireless charging, and therefore I would like to concentrate today a bit more about what wireless charging is and what role it could be for future Hyperloop applications. Therefore, I need to change now to another presentation. So what I would like to introduce to you now is what is wireless power transfer systems, especially for mobility application, and here for today, how could it be used also for Hyperloop systems. First of all, just a few words to Intis. Intis today has two main tasks. One is to maintain and keep operational the maglev test, or to find future opportunities for maglev testing facility operations. And as we already with the TR09, the last German maglev vehicle, started to learn something about wireless charging, because this vehicle was already equipped with wireless charging equipment. We converted a bit our main focus, engineering focus for today, in the direction of wireless energy transfer systems for transportation applications. So what is wireless charging, and why do we believe that wireless charging can drive the transition to pure battery electric mobility, especially road mobility? Well, later I will come to the point how it works, but there are a few aspects which obviously can help to drive transition to battery electric mobility. First of all, you do not have to plug a cable. It also supports autonomous driving and automated driving, and driving without future driving without any drivers. It is fully automated. It is invisible technology, because it's intended to let the coils which generate the magnetic field really to put under the floor, so there are no risk for let's say to have degradation on this system components, or vandalism, things like this. It's highly efficient. It doesn't require any maintenance. That's very important. And it's something which we believe could also be, we can develop a vision that also in our future cities, where we hope to have many electric cars in the road, to provide some charging technology which doesn't require all these cabling, which I think is very important. Left and right, the photographs or the pictures is something where I'm giving some examples about wireless charging. Some of them I will go and dig into in the presentation now. We distinguish between stationary wireless charging and dynamic wireless charging. Stationary wireless charging is mainly something quite comparable to conductive charging without cable, but while the vehicle is always in a certain position, so stationary. For stationary applications, we consider transfer power in the range from 2.35 kilowatts to about 30 kilowatts. It's fully enough. And or if we talk about trams or buses or BRT systems, it may go up higher, up to 300 kilowatt at least is possible. It's a charging technology where the energy flows through or via a primary coil, which is installed as a road. Road is installed only at one charging point. And this is in accordance to standardization of wireless charging. We have to make sure that the overlapping of the coils or misalignment of the coils in X and Y and driving and transfer direction we should be able to transfer the power with full requested efficiency, which is defined 85% or more, with misalignment of the coils of plus and minus 10 centimeters in each directions. The primary coils will be invisibly installed on the surface or under the surface of the road. and the dimension of the coils, especially the secondary coils which are installed in the vehicle, drive the power, the amount of power that can be transferred to the vehicle. It's contactless, free from wear, low maintenance, as I said. And the other part is dynamic charging. This is charging while driving. Fully dynamic charging is something you may imagine for in long future. The motorway from Hamburg to Munich to be equipped with coil systems, not all along the road, but in parts of the road. And when you need for your electric vehicle more new energy to recharge your batteries, you may use this charging lane, or you may not use it if you don't need to have additional or new energy for your batteries. The more interesting application for us today is semi-dynamic wireless charging. That is something like a charging lane for taxis, which you may imagine in front of an airport, where the waiting taxi, rolling, halting, while approaching to their clients, to the passengers, you can use the time on a specific lane where you can recharge the batteries, where you can operate your climate, your heating system, for example, and you can recharge the batteries. And it should not happen that if you have to wait 1 hour and you have to drive and you have to eat your vehicle, that when you are approaching your passenger, the battery is empty and you cannot drive your vehicle anymore. The power transfer rates are a bit higher for cars. We expect not to more than 30 kilowatt power transfer energy or power to be transferred. For trams and buses, it might be something between 60 and 280 kilowatts. How does it look like? In the middle, we see this. The vertical is the power path. Let's start at the lower part. So we need somehow to connect to an energy supply or to a grid. Then we have some components which convert the usually 50 hertz AC energy or current or voltage to a quite high frequent alternating current, which is usually between 20 kilohertz and 85 kilohertz. That current is driven to a coil which converts to magnetic field, and then from the road to the vehicle side, the vehicle also has such a coil. This alternating magnetic field is picked up by the vehicle side coil, is then being rectified and then fed into the battery. This is a power path. Today, if you look at standardized systems, it's going up to 25 kilohertz, to 85 kilohertz at 22 kilowatts. There's a lot of equipment which we need in addition for making sure that if there is some living object in the air gap between the two coils and magnetic field density would overcome limits as they are defined and allowed, we need to make sure that the magnetic field, in such a case, somebody scrapping in between the air gap, magnetic field will be switched off. That is what we call LOD, living object detection, and also foreign object detection, because if there is placed on the road coil directly a thicker metallic part, it may heat up too much, and that also needs to be found out and then to be switched off. This is what we call the auxiliary equipment. Then there is communication, of course, because vehicle and primary side systems have to communicate to control the power and to ensure safety of the system. There are different ways and topologies for the coils which you can install in the road or in the vehicle. Here I put an example for a so-called double D, double pole geometry, which you see in the left down view. You can install it in a different way. And on the right side, you see an example for the coil topology as it would have to be installed underneath a vehicle. Here is an example for dynamic wireless charging, which was already implemented 2009 at our facility. You see the two big black cables underneath the guideway table. This is what was used for Transrapid when it was driving lower than 80 kilometers per hour about, in order then to transfer power of up to 2 times 250 kilowatts to recharge the onboard batteries. at the time at a frequency of 20 kilohertz. Today we would go to higher frequency because semiconductors and electronics today support much higher frequencies. The pickup coils were installed in the maglev system, and there we had about 2 times 70 meter space for installing the pickup coils in the vehicle, and therefore we could also provide the 250 kilowatts. This is a way we could install wireless charging coils, for example, in the road, on pedestrian, on ground or in ground, whereas in ground is preferred today, or on the left side for dynamic wireless charging, either directly in the concrete or a hybrid solution with concrete blocks in the roads. And there are also 2 examples for how it could be done for rail application, not maglev, but for rail application, which even where the steel rods are very close to the wires, which are driven by the alternating current, would not get too warm with distances more than 10 centimeters away from it. This is the fields of application for wireless charging. I will share after the presentation to Lucas the presentation, and then he hopefully will give it to you if you are interested. Here's an application for dynamic wireless charging for taxi applications, which will be implemented with us and other partners currently in Cologne with LEVC London cab taxi vehicles, which shall run someone as from 2022. Here are some ideas about dynamic wireless charging for buses. The idea is not only to charge a bus when it's waiting for, and exchanging the passengers, but also using the whole lane, specific lane, or in front of a traffic light. And on the left side, we see such an implementation at our facility. Here are a few more photographs how inductive charging system look like, and also a screenshot to give you some positioning support. When you don't see the road coil anymore, you need to know where to go in order to align the coils to each other. Here's some other photographs. Recently, we have started for autonomous vehicles. It's a Navia vehicle from a French company, Navia, which will be equipped now with inductive charging for an application in Groningen. Top left, it's an application we have provided to Munich. This is stationary charging, 11 kilowatts, according to standards, and many more. Here are a few views also from the control room. Here you see the merger, let's say, between the old times, which is maglev, and the new time, which is a bus application, dynamic wireless charging. So thank you very much for your attention. I had to go through fast again, but hopefully if you have some questions here, I would be happy at least to answer them to you, to your happiness. Thanks a lot.
Thank you very much, Dr. Effenberger. It was very interesting. And now we already have some questions that we're happy to go through. So I'll start with the first one. The first one is, how can you make sure to reach the max efficiency also at misalignment of 10 centimeters? Yeah.
Yeah, this is, as I said, standardization requires about 10 centimeters plus minus in each direction. And there's a trade-off between, let's say, alternating current, which you need to increase if you have a misalignment to get still the power transferred. If the magnetic coupling is not that high, is not optimal anymore, you could compensate by higher alternating currents, which people do. But on the other side, we have to make sure that even if you increase, or when you increase the alternating current through the coils, that you do not exceed magnetic limits in the so-called public environment around the vehicle. So it's mainly a kind the way the coils are designed magnetically, geometrically, makes them a bit larger, would help to have more and higher tolerance for this requirement. And what we have learned, and many other companies have learned in the past too, with the right geometry of the coils, you can make it on one side to keep the power transfer, to keep the efficiency, and not to exceed magnetic field strength level outside or in the public environment around the vehicle. So it is possible to work, let's say.
Okay, then somebody's wondering, will the coils be powered 24/7 or only when cars are driving over it?
Yes, for stationary applications, of course, you first have to request, I want to charge on that side. I press a button in my vehicle, then you get a request to enter the field where the coil is. And then when a lot of safety measures have been checked out, then the charging system will start powering the coil. So only powered if a vehicle is over it. It wouldn't work in a different way. And for dynamic wireless charging is like the motor for a maglev system, that you only engage coil sections which have a certain length. You only engage the coil sections where which are, let's say, passed by the vehicle at the time. So you engage it a bit earlier than the vehicle reaches the area of that coil, and as soon as you leave that area, you switch off the coil again.
Okay, and then the last question we have is there a maximum efficiency of wireless charging? If so, what is the defining parameter?
Yeah, as I say, the minimum requirement is 85%. Those which are providing both side coils are usually covering efficiency of 90% or more. But if you have to mix the coils of different suppliers, it's still accepted to run up down to 85 kilohertz. Our experience is, and I think this is similar to others, if you make a good design, you get more than 92% of efficiency, which is quite similar to high power conductive charging system. So basically, the efficiency is not a big issue for wireless charging. How can you do that? Increasing the frequency is at one point a good matter. You can increase the frequency in order to get better efficiency, but on the other hand, as you know, proximity and skin effects then come from some frequency ranges also come into the play. And then if you further would increase the frequency, let's say above 130 kilohertz, you get so much skin effects and so on that the existing cross section of the current of the diameter where the current is can be put through then decreases again, and then you lose efficiency. So therefore, what we have learned is for high power charging in the frequency range between 60 and 85 kilohertz, it's a good frequency range to achieve also the required efficiencies. Then just to add it, it's a very simple formula to get power transferred. The power is simply the product of the two currents multiplied with the frequency. That means as higher you put the frequency, as lower the product of the two currents shall be. But you cannot increase the frequency that much because of the skin effect. So there's somewhere a limit. But nevertheless, try to keep the currents through the coils as low as possible.
Okay, thank you very much, Dr. Effenberger. I think we would all love to go much deeper now, but unfortunately, due to time reasons, we need to continue. So thank you very much for your input talk. It was very interesting.
Thank you for my presentation.
Thank you also from my side. And as you mentioned, we will share then your slide deck also for all the viewers who will collect it and also compile it by the end of this seminar edition. Also together with the videos, they will be published, of course, on the new website. Now let's come to the next speaker. This is Nico Ege. He is a student from ETH, and he will present us his rail bridging concepts and mechanisms for high-speed transport. Nico, please, stage is yours.
So I think you should hear me now.
Yes.
And see the full screen of my presentation.
Yeah, perfectly. Great.
Okay, so let's start. My name is Nico, and I'm at the moment in the last semester of my bachelor studies, and today I'm going to talk about my bachelor thesis and especially the challenges of high-speed rail traveling in the context of a rail bridging solution. Yes, we mentioned before where you can post your questions. So let's start with the overview. First, I'm going to talk about the goals of my bachelor thesis, then about the loads occurring for the special parameters we set at the Alpha Tube here in Switzerland. And I'm also going to talk about the rail joint, which is crucial for our bridging mechanism. And at the end, I'm going to summarize everything. So you probably know the situation. We have a vacuum tube on the right. There is a test track in this to the right direction, already at low pressure. And now we want to enter the test track, the tube, with our pod. The problem is now that we don't want to flood the whole test track with the atmospheric pressure, because it is a really big volume. So we install an airlock on the left side, which has a relatively small volume, and doesn't take much time to pump out the air. We do that, and then we can open the valve which separated the two sections. Now there is a gap inside the rail, which we need to fill with a bridge, and then our pod can drive into the tube. The main task of my bachelor thesis is now to come up with a solution for this bridge, which is also working for high speeds up to 900 kilometers per hour, which are the aim for the Alpha Tube test track. Yes, the problem here is we use these rails as suspension rails on the left side and on the right side. We use this standard railway rails because we want to remain a certain interoperability between the pod and the standard railway. You can imagine, for example, that we drive long distances from Zurich to Geneva or so, and then for the last kilometers or meters, we leave the track, the tube, and drive on the existing infrastructures, for example, from the SBB. That's why we chose a standard rail profile. The problem with this profile is that it has a big undercut marked here in gray. And if you imagine the valve needs to slide from above, it is hard to seal this undercut. The solution is now that we clear the valve gap here fully, so the geometry of the valve is easy and it is not hard to seal the outline of the tube. Of course, this leads to problems, and the bridge needs to withstand some loads. Now I'm going to calculate the load specifically for the case of Alpha Tube. Yeah, the total weight of the pod is 1 ton. That's the total vehicle load. Later in a commercial use, of course, this total weight will get bigger, but by adding more wheels, also the wheel loads can be 1 ton or 2 tons. Then we also assume that the total load can rest on 1 wheel. That's just worst case we consider here. And we also defined a load angle theta, which is often used in aviation. This load angle is the angle between the total acceleration and the gravitational acceleration. The total acceleration consists of the gravitational acceleration and the centripetal acceleration occurring in track turns. We set that the maximum load angle to 30 degrees. The reason for that is that also the maximum banking angle in curves alpha is 30 degrees. That means that when you're driving through a track turn at top speed, you don't have lateral accelerations parallel to the track bed. This is good for passenger comfort because then they are only pressed in the seat and not to the side. With this thing set, we can now calculate the minimum turn radius. And for our top speed of 900 kilometers per hour, we get a minimum turning radius of 11 kilometers. To have a comparison how big this is, here the big red circle, that's a full turn with a radius of 11 kilometers. And of course, if you need to drive through a city where you need to drive around certain buildings, you need to make this turn smaller, and then we also need to reduce the top speed to stay inside the maximum load angle. On the left, I've also drawn a circle which has the size of the particle accelerator of the CERN in Geneva, just to have a comparison. So now the loads can be calculated. The lateral force is parallel to the trackpad, and the normal force is perpendicular to the trackpad. And here they are shown as a function of the driving speed and also of the banking angle. I'm now interested in the maximum force inside a track turn or in a straight, and for the maximum normal force for our maximum banking angle is found here at maximum velocity. And it is approximately 11.3 kilonewtons. As we said before, the lateral acceleration gets 0 at top speed, so the maximum lateral force can be found at standstill and is about 4.9 kilonewtons. We can compare that to the static forces occurring on a conventional rail, for example, the SBB, and we can see that our forces are much lower. For the normal force, it is 10 times smaller than for standard railways, which means for the static forces, we are on the safe side for the rails. Of course, these forces need to be taken into account when calculating the stiffness of the bridging solution so that no big deformations or dislocations occur. Additionally, there are dynamic forces. These dynamic forces occur because the rails are not perfectly flat, but have slight imperfection and waves on them, which lead to accelerations of the vehicle. For the lateral force, these dynamic effects are not very important because it gets smaller with increasing speed. But for the normal force, it can get up to 10 times bigger. Of course, it needs to be observed if this force really gets 10 times bigger or even bigger. But here, a normal state of a railway is assumed, and we get about 110 kilonewtons. If we compare that again with the static force of the SBB, we are about at the same value, and that should neither be a problem. So another crucial element is the rail joint, because we need to clear the valve gap. So the two rail ends can't be welded together as it would be done on a normal railway. Now I want to define, or at least say, which type of misalignment is most suitable for our high-speed case, so 900 kilometers per hour. The first case is a vertical drop, so the second rail is lower than the first one. The good thing about this case is that from a critical speed on, about 10 kilometers per hour, the wheel loses contact with the first rail and is airborne. The advantage of that is that the impact speed here stays constant and is only dependent on this vertical misalignment here. So we get really low impact speeds and also low impact forces. The problem is, however, that this wheel can stay airborne for quite a long distance, and it needs to be observed if this has a big impact on the braking distance, for example. The second case is this one, again, a vertical step. This is the worst case of all the three cases which can occur, because here the impact force rises linearly with the traveling speed. And also we hit the edge, which means there will be high stresses inside the rail and the wheel. The third case is this one. Here, the support point of the rail is not located right underneath the rail joint, but on the right and on the left of the rail joint. This means that the two rail ends can shear and bend. For this specific case, I calculated the maximum impact force by doing energy conservation. And here on the top right, you can see again the parameters for our specific problem with our top speed and overhang length, and we get a maximum impact force of 650 kilonewtons. This is now over 6 times higher than the static forces we found on the conventional railway. So this case is also not usable for our high speeds, and we can only use the first case with a vertical drop. So let's summarize everything I said today. First, we saw that the dynamic forces grow with velocity, but as we are using lightweight constructions for our pod, we can reduce the wheel load and therefore stay inside the borders we defined. And also the dynamic forces can be lowered by freshly grinding the rails and therefore reducing this imperfection and waves, which I talked about. The second thing we saw is the rail joints, where we need to avoid a big impact on the rail and the wheel. And we saw that the only suitable case is this one, where we have a vertical drop, which leads to low impact speeds. So for the track side, it is possible to drive at such high speeds with conventional wheels and conventional rails. If we do tests and see that this this wheel and rail pairing does not work, alternatively, of course, the pod could also there could also be a levitating system installed, which can be magnetic or with air cushion, and this would not have to, then we would avoid these contact problems we have with the rail and the wheel. So that was my presentation about high-speed railways. Thank you for your interest, and now it's time for your questions.
Thank you very much, Nico. It was very interesting. So we'd like to go to the first question. And the question is, what are the highest speeds that SBB normally drive over such rail gaps? So for instance, Weichen, so switches.
Yes, so the SBB for the rail joints, rail gaps, it's 80 kilometers per hour, but for the switches, the Weichen, it is higher. It can be up to 150 kilometers per hour. And there is also an example of the SNCF, the French railways, where they did the high-speed run of the TGV, and there they run over a switch with over 400 kilometers per hour. I think it was even around 500 kilometers per hour.
It's very high.
Yes.
Then the next question, somebody's wondering regarding the airborne case you talked about.
Mm-hmm.
So the question is, can you give an estimate of travel distance for a 0.1 or 0.25 millimeter gap?
So I calculated the case where we have a misalignment of around 1 millimeter. So a vertical misalignment of 1 millimeter, and there the wheel can stay airborne for around 3.5 meters traveling distance.
Okay. And then the last question is there good literature on these rail impact physics? Can you recommend any?
So I have multiple sources. Probably I can make a list of them and we can post them on the website, because it is now hard to search this all together. Would that be an option?
I think maybe you can add the list to your slides as the last slide.
Okay, yes, I can do that.
Cool.
Super. Thank you very much, Nico. It was very nice to see this challenge of this simple rail graph bringing into the high-speed regime. Now our last speaker, last but not least, is Kristen Harvey. He's partner of the NOS Design Experience, an agency that has a lot of experience with rail industry and their designs, interior, exterior. Very much looking forward to the talk of Christian, how to cater the passengers for such vehicle design. Christian, the word is yours.
Thank you, Fabio. I will share my screen. Let me see. I think you might see a lot of red now.
Yes, it is.
Wonderful. Okay. Okay, welcome everybody to my talk. The title, as mentioned, is How to Cater for Passengers in Fast-Moving Vehicles. Alternatively, I was thinking of changing the title to It's All About the Cross-Section. But first, a few words about us. So you might not know us. As mentioned, design agency in Zurich. We are on the tracks since like 30 years. We have on board 28 design experts, mostly industrial designers, a few other disciplines also, like graphic design. We have designed so far about 90 trains. Well, I have to admit, not all of them have been built actually, but at least we have designed them. This is one of those that has been built. This means that we do some interior design, including sometimes the seats, if possible, and also the exterior design, sometimes also including collaboration with the aerodynamic department. Quite interesting stuff. I like a lot. Our first contact with the railway industry was, it's quite a funny coincidence, in 1999, when we came in contact with the magnetic levitation dream. At that time, the TR08 and the TR09 in Laten, we had the unique opportunity to do the industrial design of the interior of this wonderful experiment. And what we found out later, together with the TR09, it was kind of a, I would call it a Concorde on rails. I mean, it was in the beginning, magnetic levitation was a dream, a thesis, kind of, and it was proven. In the end, it did work quite good, but it was too expensive. So that's why I compare it with the Concorde. It did work in the end, but somehow it never became a commercial success, because despite the fact that it worked, it was too expensive. In the case of the Transrapid, it was political and commercial at the same time. So when I was looking at the current Hyperloop ideas and concepts, I was looking also at the interior design, or the stuff you see on the internet. You see studies, mock-ups, one-to-one. Here on the left side for Dubai, I think, they did actually build a nice mock-up. Here on the right side, it's just a rendering. And then there was a study of Teague Associates, also industrial designers. And I looked at all these pictures and I thought for myself, okay, this looks quite okay-ish. But on the other hand, I've seen that Elon Musk, in the original paper, I assume, he was talking about inner diameter of the pods to be 2.25 meters. And that was even the larger pod he was talking about. He was talking about the even smaller pod, which was dramatically smaller. So I look at these pictures, I say, oh, wow, this looks more like a little bit more than 3 meters diameter. And so I thought for myself, obviously, this is a unique opportunity for the whole industry to make a clever and strategically sound decision on what is going to be the best diameter for this new exciting technology. The current trials are done with really small pods. I think you're all familiar with this one. And so I was thinking maybe it's a good idea to look a little bit sideways. What is other industries doing, or what have they been doing? So I was looking at or trying to make an interesting comparison with the commercial airplanes. I would say commercial aviation is happening since roughly 80, 90, 100 years. So they had a lot of time to optimize the technology. And there's a very capitalistic system behind. No, in most cases, there are no subventions from the state. So somehow it's like an evolution forced by commercial forces. What is reasonable depending on the spectrum of usage. So I was looking on the internet on what are typical cross sections of airplanes. And obviously you start with very small diameters where you don't even have an aisle. Obviously you should not do too long tubes like that because nobody would be able to enter properly. Then you have next step a little bit larger where you have your kind of an aisle. Then you take a next step and have one aisle. Obviously you waste a lot of surface if you look at it from the ground floor, or if you look at the diameter, you waste a lot of cross section just for getting to your seats. Things improve when you go to larger diameters. But to give you an example, if you look at cross section 2x2 arrangement, 3x3 arrangement, you never see a 2x3 arrangement. And then if you go further from 6 in a row to 7 in a row, you discover, oops, you need a second aisle. And then you make a jump from like 4 meters something to almost 5 meters. So obviously there, you cannot like scale it smoothly as you might want to, but you have to decide, are we going to start with a proper diameter for the pod and then deduct the diameter of the tube, or do we go the other way around and look on the market for tubes which we can buy just as ready as they are? And so I came back to railways and was looking, okay, what happened actually in the railway sector long time ago? And if you look into history, we have certain standards developed regarding kind of expectations from the passengers. If you look at what's happening on the market nowadays, you could simplify it to break it down to these requirements. So like typical passengers think up to 10 minutes standing is okay, 10 to 20 minutes, a perch seat, a bum rest would be needed. If you expect to travel up to 30 minutes, people want to be properly seated. They want at least have not such a comfortable seat, but it should be a seat. If we go to 120 minutes, we end up with intercity seats with tables. People want to work, listen to music, watch videos. They will need a toilet. They will take along larger luggage. So you end up if you increase the travel time beyond a certain measurement, you end up with all this list of amenities you have to provide. Things go absolutely out of hand. If you go up to 600 minutes, 10 hours, you definitely will need a restaurant. Otherwise, people will have a little revolution on your train. And if you go above 10 hours, well, obviously you need beds. People want to go to sleep and so on. So now what we are currently talking about is like Elon Musk talks about 35 minutes. So we are somewhere around here. Critically for us will be toilets and luggage shelves. Is it going to be necessary to provide toilets? It's like who depends on what kind of passengers you want to talk to. If you talk about elderly people, it might be an absolute requirement. Then in the railway market, we have certain standards where almost everybody has agreed upon by now. And I call it like the 900 by 500 rule. Roughly, everybody is more or less happy if he gets like 900 in this direction, which is much more than in a typical airplane, and the width of 500, 520, 480, depending on comfort. So then we have in the railway market also quite an interesting problem that we have some laws. We cannot do what we want to do. There's a European law. If you have a regular schedule of a public transport, you are required to have at least 10% of all seats. They have to cater for the needs of persons with reduced mobility. We call it the so-called priority seats for PRM. For example, this is a picture out of the norm. So they require you to provide certain spaces. They require you to, that the armrests have to be foldable. You have to fold them up. If somebody is very heavy and fragile, you have to fold up the armrest and so on. So typically the SBB, Deutsche Bahn and ÖBB, what they do, they provide everybody this comfort. Otherwise, it would be too complicated to make a distinction between those seats and the special seats. Then the big question, what is okay, socially okay? Is it okay to sit 3 in a row? And if you do that, do you enter along the train at certain points in the train? Are there going to be 1 aisle, 2 aisles? How many doors? Quite difficult tasks. If you have a pressurized cabin, if you look at a typical airplane door, it's quite a construction. So you don't want to do too many doors, and probably not necessarily sliding doors. This is just an example found on the internet. Then together with other railway projects, we found out it's always the infrastructure that is dangerous, meaning it's expensive. And so that's where I come to this big decision point. In the early times of railway, there were a lot of discussion on the proper track gauges, a lot of discussions on the proper structure gauge. This is kind of the cross section of the tunnel you have to go to fit into, and it's kind of the minimum clearance outline within this line every train has to pass through. And I give you a little example. If you compare like a little 1 meter track railway up in the Swiss mountains, the 1 meter allows, together with the slow speed, that's something really important, together with the slow speed, to have small radiuses, which means you can follow the terrain quite easily. And that means you have smaller bridges, smaller infrastructure cost. And if you compare it with like a typical high-speed train of today, if the terrain is not so suitable, not so flat, you have a sequence of bridges and tunnels and bridges and tunnels, nothing else. So these things get really expensive depending on the speed, which we are not going to alter in our project, I think. But nevertheless, the cross-section will play a part in defining the cost for the tunnels and the bridges. A really bad example on extremely expensive infrastructure you find in the Japanese maglev, where they have chosen quite a hilly test track area, which is like an amazing. They have built like 40 kilometers of only bridges and tunnels. So how would the cross-section look if we designed according to the rules of the railway industry? And so I started with a typical railway seat with the typical dimensions, typical aisle width, which is also required by European law. And then I tried to fit the smallest possible diameter around it, leaving the extra space for lighting, the yellow stuff, fresh air, old air ducts, the blue stuff here, and maybe squeezing in a really small toilet. Could work like that. It's not really, people will not be so happy. It will not look as beautiful as the renderings we have seen before. You have to imagine when you walk through this aisle, you will have your head in this really confined space. And then if you want to sit down, you have to hunker down and kind of squeeze into this area. But well, that could be done. And you would end up with a cross-section of, let me see, 2,800 on the inside in a tube. And according to what I've seen on the internet, currently there's a proposal to have like 146 tube diameter of the pod. You would end up with a 4-meter tube. And if you think, wow, this is crazy, don't forget, you will need some doors. You will need some space in direction of travel for the toilet and the luggage. And you will lose quite like 50% of, no, you will not lose. You will have to add another 50% of the actual seating area to just include these things. So that leads to the idea, maybe it's a better idea to have like 50 seats in one pod. So 50 people would share one toilet, and that would improve the overall efficiency. If you squeeze even further, you end up with wasting space here, because in this case, I choose the diameter so that we still have this aisle height, which is required to be 2,000. And so if you take this as a given thing, you end up with a diameter of 2,480 on the inner side, and will have a diameter for the tube from still 3,630. And if you look at this situation, well, considering length, you lose a little, you have to add a little bit more, 37%, but still, it's still the same thing. Make it longer and you will improve efficiency. You could make it, but you cannot always make it longer and longer and longer, because in the end you will need a second door, and then you have to put in extra space and wait again. So it's a really a fine balance on finding the optimum. So this is the end of my presentation. Thank you. Any questions?
Thank you very much, Kristen Harvey. It was really very interesting to have such an insight, besides all the otherwise very technical focused topics. So I would like to dive into the questions. The first question is, you also consider psychological aspect when designing the interior? How would you solve, for instance, the problem of not having windows in the pod?
Yeah, good question. The simplest solution would be to make a large diameter, like something our colleagues here have already looked at. If you look at this looks quite airy. This blue stuff would be some backlit surface in the ceiling. You will not see outside, but this would give you like a airy, open feeling. And also, if you look at these details, you have some light coming out of the wall. There are some measurements we could take to give you this kind of cool feeling in such a pod. That's no problem. It's just what you see here is a good example. They're pulling all the tricks possible here.
It looks very nice. Then somebody's wondering, how much can you pack people? What is the metric passenger per cube meter? I mean, I think the question is there like a rule or a law for this? Yeah,
it's quite simple. It's like you have to just follow this rule, 900 by 520, and then you go like here. You arrange them like that. If you go crazy, you squeeze it to 800, and then you might add a third one on both sides, 6 in a row with a small aisle in between. That's more or less the maximum. And then you're looking at some Ryanair flying to Mallorca. It's like that kind of stuff, like this kind of arrangement with a pitch of like 800, something like that. But well, the market shows that people often think about the price first, choose Ryanair or EasyJet. It's less expensive, and then they discover, okay, shit, I have to sit for 4 hours in a really tight space.
Okay, then we have 2 questions which are quite similar, so I combined them. So 2 people are wondering how the seats will be designed. So one person is wondering, will it be like a tram or metro seat? And the other person is wondering, will it be like bucket seats in fast cars?
That's quite an interesting question. It's like if you want to put some G-forces, lateral forces and longitudinal forces, then we will need some kind of a racing seat. But well, yeah, it's like a marketing decision. You either have like a roller coaster feeling, pretty exciting, a lot of acceleration. You get a racing seat, you feel like sitting in a Porsche without windows. And then you hurry up and you're fast. And then you just look into your iPhone or whatever, and it's small. Or the advantage of current railway travel is you can stand up, you can walk around, you can have a phone call, you take out your laptop, start working, and all these things, which are not possible in a kind of a confined space with racing seats. Yeah. And also there, I see a clear distinction. When you go above 30 minutes, I think things start to change. If I go a train for more than like 15 minutes, I start working on a train, on a current train. So other people wait for a little bit more maybe, but it's really, if you're sitting 1 hour in a train, you want to have some comfort. You might want to sleep. You need a comfortable seat and something to drink, laptop, music, video, yeah. And then you change a lot of things. Then you should change actually even the acceleration forward and sideways.
Okay.
And then you have the whole problems of the laws. Like in European travel, it's if you have a regular schedule, and then you have the Bundesamt für Verkehr, the Eisenbahnbundesamt, and so on, and they have regulations, and then you have the Behindertengleichstellungsgesetz, and you have to provide everybody the same comfort, and then you have to be able to have a lot of space for wheelchair users, extra space for people like that, and then you have certain angles required, certain seat height is required. Grab handles are required. So in the end, you will end up something similar like a railway seat. Maybe a mixture. Maybe you would pay some extra money to make it lighter than a railway seat.
Yes, it's very interesting to have an insight into these topics already. So we would like to thank you again for the interesting talk. I'm Kristen Harvey.
Thank you very much. Pleasure on my side.
And also thank you again to the other speakers tonight. It was very insightful. And yes, we have the next seminar in a week, and we look forward to seeing you all again then. As mentioned earlier, you can find the recordings and also the schedules for the next seminar sessions on our website. It's vacuumtransport.org. You can find everything there. And yes, in the name of all the organizations, we wish you a nice week and see you next week. Have a nice evening. Bye, everyone.
Good.
Bye.
Okay,
See you next week.
Bye. Thank you all.
Thank you. Bye. Bye.